Okay, so I wrote down 5 formulas here, so tell me what you tell me about them. And we got some good stuff, some context. I didn't see in most cases a whole lot about that gives me confidence that you really know how to apply them in a situation. Okay, really know how to use them in a problem-solving situation. Okay. But it's on the right track. So we got to nail it down. Got to nail it down. Okay, well, this is pretty good. This is pretty good. Okay, because we know that this, of course, is velocity, the rate of change of position. This is acceleration, the rate of change of velocity. Okay, so this is position, rate of change of position. And this is rate of change of velocity. The acceleration. So if you want to give me a little more complete picture, you would say okay. And then you might even indicate that this whole development can start down here and go up here using integration. That's how we derive this formula. Now, knowing this is good. Knowing this too is what you really want to have nailed. Because then, if I give you some other acceleration function and ask you for the velocity and position, you got to know to integrate. And if you remember how to do the integration constants and what V naught means in terms of that process, I have to review it, did it very early in the semester. But if you have that process, then you're going to have a good understanding of your equations of motion. Now, what does this have to do with this? Okay. Well, if you eliminate t between this equation and this equation, you get this equation. Okay. Also, well, that's enough. Solve this equation for t. You get t equals v minus v naught divided by a, right? Plug that in up here. You get x equals all this stuff. You just plug in for t. You don't have to square that expression here and here. Then you rearrange your variables a little bit and you get this. You should be able to do that for the 4 equations of uniformly accelerated motion. Once you have this, you just got to know what simultaneous equations to solve. Okay. In order to get what you have. Okay. So anyhow, that's good. That's a really good start. Take it a little further, and you have a good command, and you actually have a unified theory of uniformly accelerated motion with 4 equations. You'll solve any problem in which motion is uniform. Because motion is uniform, you always have an initial velocity, okay, an initial position, an acceleration, and time involved between any 2 events. It's actually 5 variables, 6 if you include x naught. And the equations work very elegantly. If you have 3 pieces of information, using the equations, using only one equation, you can get one of the other quantities you don't know, and then use probably any, maybe 2 or 3 equations to get the remaining quantity. Okay, that's uniformly accelerated motion. That's how we model it. That's how you need to have been solving problems involving uniformly accelerated motion, including projectile problems, where you have an x and a y. And you might want to make note of that. Yeah, watch this video, take some notes. If you have y's, well then, for uniformly accelerated motion, for projectile motion near the Earth, neglecting air resistance, your acceleration is g downward. So maybe negative g times the j vector. Okay. And your x is characterized by no acceleration because there's no force acting in this direction, only this direction. Again, we're ignoring everything. You write down two equations. You write down x of t equals this, y of t equals the corresponding thing. You put a subscript x on this, and it's probably not a bad idea. So put the x subscript in these. Okay. So that if you're in a motion situation in 2 or 3 dimensions, you don't accidentally use x quantities for your y motion or your z motion. Okay. But you just write down this equation and then the equation where all the x's are replaced by y's. That models here and then you can set ax equals 0 and ay equal to negative g. Okay, well, there's that. Okay. You correctly identified this as rotational kinetic energy. Okay. This I thing seems to have kind of escaped you, although you came up with this. Okay. Now this is center of mass. And really your picture here isn't quite right. First of all, R1 and R2 have directions. Okay. And you can measure R1 and R2 from any point you wish. So just take any point. This is not necessarily the center of mass. So I'm going to correct this just a little bit. So let's say we if this vector represents R1 and this vector is R2, then the torque here is M1G R1. It's a positive torque because this weight here is going to tend to rotate about center mass in the positive or counterclockwise direction. Okay. Torque here is M2G R2. And now your center of mass is going to be at this position relative to this point. So if this comes out, I'm sorry, about the direction, this is a negative torque because counterclockwise. Okay. And there are ways you can deal with other. So that this is the position of the center of mass relative to this point. So if this number is positive, that means you're to the right of this point. If it's negative, you're to the left. And you can extend this to any number of masses. And then you can extend it to an integral. Okay? Your numerator here would have a G on this term and a G on this term. But then you'd also have a G in the denominator here, so the G's would all divide out. Okay, so you don't need the G's. Here's your sum of MIRI over the sum of your MI, and that approaches the integral of MR, say ds, over the integral of using M. We don't have a lot of time. Delta R dx is the integral of this delta dx. If you integrate you are there, you just integrate delta with respect to x on a typical increment. Delta is gives you an approximately constant density. You multiply that by your delta x and you get the mass of that increment. So just adding up the masses of your increments, that for a continuous distribution, we get this. And here, for continuous distribution, we get this. And that's when you learn the multiplication calculus. We need it in the chapter on equation. Okay? Those are moments. For reasons that we've talked a lot about in lab, they're related to the work done by a torque. Okay, there's the torque. The kinetic energy, or the kinetic energy is I omega squared, where I equals the sum of your MR squared, not MR. Okay, and it's not divided by the total because you're not doing center mass. This is net torque over mass. Okay. And saying there's a G in the denominator here really isn't. Right. I'm going to kind of wave my hand. Okay. Okay. So you would have this kind of number. That's your moment of inertia. You got to know. Moment of inertia, then, and you're on the right track to say, you know, something's moving, it's got inertia. Yeah. If it's moving more, it's got more inertia. It takes work. Or there's a change in momentum. There's not everybody this. I never saw the word momentum, but we did see the relationship to collision, right? So this is the impulse momentum theorem, which you ought to be able to immediately state. Okay. No, when you see this, or when you see a collision, you know impulse momentum is involved, and here's your impulse momentum. And this, of course, we've written as delta T. Also, works fine in more than one dimension. So we can make F and your velocities and your momentum vector quantities, and they behave as vector quantities. Okay. So this is rotational kinetic energy. I'm not going to get into the derivation of it. There's some time, but you just figure out. Well, you got to understand the relationship between torque and acceleration. So I'm going to skip down to this. And of course, the torque vector quantity, the angular acceleration is vector quantity, so it's torque. Right-hand rule determines the direction. Torque and the angular acceleration are the plane perpendicular to your plane of motion, or the direction of your binormal. In a multivariable calculus situation, you don't need to know that physics. Okay, so torque. is r cross f, where you have the right idea that your r would be this. Okay. So if you're exerting a force out here, instead of having a mass, you know, you have a force off in some direction, and you do r cross f, getting a torque in this direction. Over here, you'd have an r cross another f. If your f is in this direction, then your r cross f would be out here. If it's in this direction, your r cross f would be like this, and you got to understand the right hand to see that. And you got to have that to be second nature. So you really want that. Okay. Up here, velocity. This is velocity. This is a simple harmonic oscillator. I didn't see the word simple harmonic motion. Probably would have understood it. Could have dragged that out of you, but you should immediately think simple harmonic motion because that's your context. Now, you drew this and you drew this, which is very good. Okay. This would be a picture of position versus time, or velocity versus time in this case. You would have, okay, you talk about an amplitude A. Well, for the velocity, your amplitude is omega A. Okay. So you would want to put an omega in front of that. For position, A is your amplitude of motion, and that's what you're thinking. Okay. But if you are modeling velocity, it's omega A. Okay, so over here, you have your circular model. You'd probably want to put omega t in here somewhere. And you probably want to put your radius, which is not A, but it's omega A. Okay. So with just a little modification, you've got a good picture. I mean, you've got a good picture, but you can add to it to increase your insight and get you in touch with things you're going to need to solve the problem. Okay, so omega t is not equal to RAD, but it's in radians. That's okay. If pi over 2, if you're at pi over 2, that means you're like at this position. Okay. Then the sine is 1, which means this is going to have its maximum possible value. Because the sine has a value that runs from -1 to 1. Okay. The maximum magnitude of the sine is 1. And that occurs here. Right. And I think we understand that. Now you did an example. Okay, so you got 10 centimeters. Then 10 centimeters times 15 what? Okay. You want to use units. Of course, you do have some units up here, and that's a good start. Okay. And then you multiply this 10 centimeters times apparently 15 radians per second. So you've got that up here. Okay. So that's good. So that's, well, 15 radians per second is omega. 10 centimeters is your amplitude that you're assuming, so you can get a handle on this. And that's a good thing to do. Put some numbers into it, think about what they mean, play around with it, then deepen your understanding of symbols and how they apply. Okay, so omega A is this. It's 650 radians per second. Okay, well, that's a lot of radians per second. It's about 25, a little less than 25 cycles per second. So this is moving around fast. If I move my finger that fast, it's going to create a sonic boom. So you don't want to be here. Okay, so I try to restrain myself. Now, you got that? Okay, so that's a good model, but you of course want to put it into the picture I gave you yesterday. The circle and all the vectors and stuff like that. And think about what they mean, because then it gives you a good picture of the whole thing. Other things that you might have seen, corollary things, if this happens, if x equals a cosine of omega. In this case, it would be negative a cosine of omega. That would be associated with this because this is a derivative of x, the rate of change of your position. And then your acceleration is going to be omega squared A cosine of omega t. Okay. And we can note that that equals negative omega squared times your position. Units work out, positions in centimeters. Omega's in radians per second. So you got centimeters times radian squared per second squared. Centimeter times a radian squared, because a centimeter of arc is what you get from a centimeter of radius and a radian, and vice versa, as we talk about. So you multiply radians by position, you pretty much get position. So omega squared x is going to give you centimeters over second squared, because omega squared got that second squared. So units match here, because radians per second times centimeters gives you centimeters per second, right? And of course, you have that implicitly in the units over here. And they said it has something to do with this. Well, what it specifically has to do with is x or y in this case. Well, but we're using x. So if your x-axis is like this, then the positions of your oscillator are x. So it's like down here you have position x1, up here you have position x2. And this displacement, well, you don't usually want to put a double arrow in things. You want to think of a vector. This vector would be x2 minus x1. So you're thinking about it. And I think when you thought about it, thinking about the experiments we did last week with the cup and the dominoes and all that stuff. Then you want to, for the experiments we did, you really want to pull all your data into these pictures and analyze it if you haven't. Make sure you understand how it's analyzed, because that gives you a very tangible connection to all this stuff. It's very valuable when you try to solve problems, as you're going to have to do. I've got about 2 minutes before each one has to leave. So this is right, total gravitational energy. You could note that gravitational potential energy is negative big G, big M, little m over R. It's equal and opposite to the work done by the gravitational force between 2 points. So it's related to the gravitational force, which has a magnitude of negative G, big M, little m over R squared. If you integrate this, you get big G, big M, little m over R, which is the work done by the gravitational force, but the potential energy is equal and opposite to the change to the work done by the gravitational force. And then you have the kinetic energy. Centripetal acceleration equals A gravitational acceleration. Running out of room here. I'm finding that my planning of things on the board is about as random as it is when you're brainstorming on the board, and I've got to insert stuff. So it means I have no skill at that. And I can't expect you to have anticipated what I was going to write. I didn't even know what I was going to write. I had to know what I was going to see. So centripetal acceleration. Okay, you probably can't read that, but when you set centripetal equal gravitational accelerations and solve for V, and then plug into 1/2 mv squared, you get the kinetic energy is 1/2 big G, big M, little m over R. Okay, when you add these, you get this. When you add these, you get this. So that is your total gravitational energy, that's fine. If you understand that, and it's a fairly simple derivation that reinforces a lot of things, then you're going to be able to answer a lot of questions that arise when we talk about these circular orbits. And this is also a circular orbit. I'm going to talk about what this has to do with the collision. I'm going to pause for a second. Okay. One person had to leave. We'll be posting this. So where was I? I was talking about this. You know, that's a context. That's what you got to understand to really understand this formula. And to use the formula, you better understand what it means and what it tells you. I'll also comment that you've got a graph. See it. Okay. What's that graph mean? Well, this is R and this is your energy. And you have a similar graph for the potential energy that looks just the same, but it's twice as far here. And we did all that. We constructed, and this graph is equal and opposite. Kinetic energy graph. So kinetic energy graph is equal and opposite. It's up here. Your potential energy graph is twice as far from the x-axis down here. So just a steeper version of this graph with the same asymptotes. And if you add that potential energy graph and the kinetic energy graph, then you get this. And you want to think about that. You want to try to understand what I just said. It's not a, turns out for some reason it's not all that easy because, I don't know. Seems like it should be easy because it's very geometric and graphical, but again, nobody does anything with geometry anymore. Ridiculous. Okay, here we have, this is impulse momentum. Okay, so we would hope that one would. Here's your impulse. Here's your change. In momentum. Of course, we use P vector to indicate momentum. I think I already said we can make these into vectors. I originally wrote it without vectors, which means in one dimension it works. If we go into higher dimensions, we want to emphasize the vector nature of these things. That's a lot like F delta S, okay, which is your work, which is not a vector quantity, okay, because it's F dot delta S. And this is an F bar, meaning your average force times delta T. I'm not quite writing this correctly. I should have the bar over the whole F delta S, but okay. And the average of your F delta S between two events is the work done between those two events. If this is a net force, it's a net work, and it's equal to the change in kinetic energy. So, you know, and that's the beginning of wisdom here. Okay, I hope that's showing up. I think the focus is remaining good. I'll focus the camera in various parts of the screen at the end. And I might go over a briefer version of this. So it's not all I could say. Oh yeah, and collisions. Okay. If this is mass M1 and this is mass M2, then the force exerted on mass 1 by mass 2 is equal and opposite the force exerted on mass 2 by mass 1 by Newton's third law. Okay. And I'll just write N third to abbreviate Newton's third law because I don't have room to write anymore. And that implies that delta P that is 0 if the system is isolated. By isolated system, we mean these are the only forces involved. Interaction force is all you have. If you got two pucks sliding on a table with friction, and friction force intervenes, and this isn't quite true. But for the very brief instant just before collision and just after collision, it is pretty much true because friction doesn't have time to have much effect in a short time interval. Okay? In other words, friction would have a very small impulse because if the collision occurs in a small delta T. Now, after the collision, that your energy gets dissipated, your velocity changes, and your momentum changes. Okay. Well, there's more I could say. I'd like to kind of derive this, but I've already done it. And you just kind of got to review it or read it in your textbook, make sure it gels, or next thing you're going to miss. Well, it's physics fun. It's likely you're going to miss things. Hopefully not, but it's going to be a challenging final. And it's almost inevitable that everybody's going to miss stuff. But the less you miss, what are you going to do? Okay. Okay, now we've got a question related to coefficient of friction. And you got a block on an incline, which can be drawn like this, or can be drawn like this. Okay. And you can change a block so it matches the incline. If you're going to change the incline, you probably want to have it like this, but it doesn't matter. The block has a mass either way. You have I'm just going to call it negative mgj, put it in the context of vectors, because taking a static flash or taking multivariable calculus, the vectors should actually help clarify things rather than cause you to have to wave your hands over things. Okay. Well, what other forces do we have? Well, I could ask you, but I think you'd be able to answer. And actually, I put my M in an awkward place. Okay. Let's see. There's a mass M. Okay. What forces do you have? Well, you have friction, which is equal and opposite to the direction of motion, or equal and opposite to the other forces in this direction. Okay, because if the coefficient of friction is high enough, this is going to be stationary, and the frictional force is going to just be equal and opposite to the horizontal component or the x component of this force. I will see that in a minute. Okay, you also have normal force, which is why this thing doesn't fall through or whatever. And the normal force, as we've demonstrated, is perpendicular to the incline. And I'll write that as F norm. You do F sub n. Okay. Now, if this is an equilibrium, then all these forces add up to 0. Okay. So let's think about that. You got your force of friction. Magnitude of your frictional force can't be greater than mu times F, your normal force. Okay? Now that gets into the idea that you have kinetic friction if it's moving, which is the coefficient of friction would be less than if it's stationary. Okay? That's why if this thing's stationary and you nudge it, it just might take off. Because the coefficient of friction suddenly changes. When you nudge it, then it starts moving. That's important to understand. Okay, well, let's just go back and look at equilibrium here. Now, to analyze this, we impose the coordinate system. X-axis here. Now things are getting confused. Let's make sure we understand that this vector here is your frictional force. And I'm being a little careless because frictional force is also a vector. And I kind of want to be specific about this. Okay, without the vectors, this is a magnitude of mu times normal force. It has to be greater or equal to friction. Friction has to be less or equal to that. Okay, so there's an x-axis. We're going to slap a y-axis on here. And then we're going to do exactly what we can think of. All everybody else tell you to do. Maybe. And do the horizontal or the projection onto this axis and the projection onto this axis. Okay. At that point, we take the appropriate color chart and cross out this force and replace it by this force and this force, which together are completely equivalent to this force. If you're pulling up here and don't see what you're pulling against, it's going to feel exactly the same if these two forces are acting as it would if this force alone was acting. It has exactly the same effect. Okay, so now we have this picture. We have our x-axis, our y-axis, our normal force. And our frictional force. A little longer here. Okay. And then we have mg, which we're not even going to write. We're going to write mgx. Okay. And mgy. And at this point, I realized that idea, right, this is mgj, because we've imposed an x and y axis where j is in this direction, not this direction. So pretend I didn't do that. Okay. So what we then say is that the normal force equals mgy, or the normal force times your J vector is negative mgy times the J vector. Okay. So the magnitude of F norm equals magnitude of M L and the arrows rotation again. And there's a negative there. So the magnitude of this is equal to the magnitude of this, since they're equal and opposite. So that F norm equals mgy. Okay, well, there's usually an angle involved here. So this angle is theta, which is typical. Then if this is vertical, then theta is the angle between horizontal. X and Y are no longer vertical and horizontal. You set them up this way so that this component is equal and opposite to this one, okay? So you got the horizontal, and here's your theta. Okay. So mgy is what? There are ways you can do this. I've done it a different way. This is probably the way you're seeing it in your statics class. If this is theta, then this is theta. Okay. And remember that mg, the one we crossed out, is down here, right? It projects here. So you get this right triangle where this is equal to mg, okay, times make sure I got this seems odd. I've got theta there. I want to say it's times the sine theta, it's cosine theta. Make sure theta is the angle here, it's the angle of the x-axis with horizontal, so that's got to be it. So this angle being with vertical and this being perpendicular to this, mgy, yeah, that's right, I don't know why. Okay, that's mg cosine theta. Don't want to write that down mindlessly, okay? Think it through the way I do, so you don't mindlessly write down something stupid, okay? Something I'm prone to do if I don't check myself at every step, okay? So that's your normal force, magnitude of your normal force, okay? The mgx we could call well, I'm not going to call it anything. Call it mgx. It's mg cosine theta. Okay, that's sine theta. So, see what I mean by stupid? Okay, so there it is. And at this stage, well, friction is again, less than or equal to coefficient of friction times your normal force. So your force of friction is less than or equal to mu mg cosine theta. At that point, you got to make comparisons and decisions. Okay. If mgx is greater than mu mg cosine theta, that means this force is greater than the force friction can exert. In that case, the net force, now remember that these two forces are equal and opposite, they contribute nothing to the net force. And of course, the reason for that is presumably you have no acceleration perpendicular to the plane. All the accelerations along the plane, which means there are no other forces involved other than the ones we sketched here, and that the plane is strong enough to support them, which is relevant in statics. You don't want to build a ramp that people fall through. Okay. Net force then is, in this case, negative mgx minus that's mu mg cosine theta. I didn't leave myself enough room as usual. Okay, gotta have a voice stretch. If you find one, bring it in. Give you a couple once in your second. Okay, that's safe. Not that I wouldn't want to do that. Okay, so that makes sense. Sort that out. That's maybe not the way you've seen it in statics, but that's the way it is in this course. And that might help you understand what you're saying in statics. Now, the other thing is, okay, F net is 0. Because that means friction is enough to hold this thing stationary. Or if it's already moving, well, yeah, there's a condition here. If it's stationary, and mgx is less than this, then you have it's stationary and there's 0 net force, it stays there. So that the force is 0, and you remain stationary. I didn't leave myself room to write down here, so I have to write up here. So I'm going to take what I would write here and write it up here. Okay. Then your net force equals negative mgx. I don't know why I say. I mean, I need the mu in here, right? Okay. That's mu k mg cosine theta. That means that this force is less than this force in magnitude. So you're going to have a net force in that direction. If you have smaller force here, the larger force here, you get a force. Okay, so then after that is negative mgx. Well, the same thing. Is negative. In case the object goes to rest. So, you know, there's plenty of friction here, but I give it a push. It's going to keep going a little ways. It's going to come to rest. Okay, let me pause this and see if that helps and see what questions you have, what other clarifications you might want.